Okay, as we begin, let's first understand what this course is about. So I'll try to explain this in terms of things which are already familiar to you. You have written programs, you have run programs, you have worked with them, and programs talk of expressions which do computations. There are data of different types which are used uh, to organize the flow of control. You use conditions, decision making, and you have iterations and loops. You write functions for abstracting the computation. If you're using object-oriented programming, you would define classes, or if you have concurrent programming, you will define threads and so on. So these are the concepts which are involved when you write program. On the other hand, the hardware, which essentially circuits, basically consist of transistors. Largely, bulk of the electronics is in the form of transistors, which relate voltages to currents. And as abstraction, we talk of gates, which deal with logical values of ones and zeros. And then further components are defined in terms of gates like flip-flops, registers, memory, sorry for that spelling, ALUs, finite state machines, and so on. So how does a circuit, which is made of all these things, uh, provide you the programming environment? How do you run program over such a circuit? So what lies in between is the computer architecture. So this is the gap we are trying to study, not entirely, but uh, to a large extent. So now also imagine that you have a variety of programming languages, C, C++, Java, Python, MATLAB, and what have you, which all can run on the same hardware. Okay, so how does the circuit take care of variety of languages? That's another question. Now, if you look deeper into this gap, you would notice where hardware and software actually interface. So from software point of view, uh, you have some basic operations which are defined as instructions, machine instructions. These are basic commands or basic operations which a machine or hardware can execute. So any high-level language, whether it is C++, Java, MATLAB, has to be related to these machine instructions. Now, these machine instructions are implemented using the major hardware components, registers, adders, and other memories, and so on. And it is at this interface that lowest level of software abstraction, which is in terms of machine instruction, and the largest possible building blocks, that the bottom, as we discussed, are transistors. So you have hierarchy of these of this buildup, or hierarchy of abstraction. So once you have defined such components, how do they actually provide you abstraction of machine instructions? So it is this interface which is going to be our focus. So we need to understand what could be the basic operation in terms of all languages could be mapped, and given these basic operations or basic instructions, how can we build hardware which will uh, provide those instructions? So let's look at a small example. Suppose you write a function like this in C. Okay, it swaps two elements of an array. So array is V, and we want to interchange vk kth element and k plus 1 element. All right, so you would take help of a temporary variable where you transfer one of the elements, then transfer second element into the first one, and then the one which was saved in temp is put back in vk plus 1. Now such a thing would be broken up into several machine instructions. Okay. Uh, so I'll not go through these because we have not learned these. But just imagine that this would be broken up into basic steps where you are either performing one simple addition, a multiplication, or loading, storing, and so on. Okay, so it is broken up into a sequence of machine instructions. Now here these instructions I've written in a symbolic form, in textual form, and language which defines this is called assembly language. Okay, uh, there is a close correspondence between these instructions at assembly level and machine level. So what I'm showing here is hexadecimal code of various instructions. So how do we get that? Don't worry about that here. So each instruction has some numeric code. You can write that in binary, decimal, hexadecimal, and so on. So basically, uh, this program is broken up into simple elementary operations, and each operation has a numeric code. Okay, what I'm writing on the left side in this description are the memory addresses. So at address 1000 in hexadecimal, you have an instruction which is coded as E00304995. So these are all hexadecimal. The next address is uh, 1004, and the next instruction is this, and so on. Uh, Now here, one very subtle thing you must realize is that the program is stored somewhere. So these are memory addresses of memory cells. So in consecutive memory locations, you have a sequence of numbers which are stored, and that represent program. So although it might appear trivial that yeah, after all, program has to be stored, but it is this concept which distinguishes a computer from a simple calculator. Okay, a simple calculator, you ask it to do addition, it will do addition. Then you ask it to do multiplication, it will do multiplication. But here, the ability to store a sequence of operations provides a power which computer has. Okay, so we have seen correlation between machine code, assembly language, and higher level language. Now, what does the hardware look like? So we'll study this in detail, but let me just give you a brief glimpse of what it is. So broadly, you can imagine that there is a memory where we would store these numbers that constitute a program. So we store the program there. And then there is a central processing unit, or CPU in short, which will actually act on these instructions. So these obviously have to be connected, and we call it a bus. In actual practice, if we look into detail, it may be broken into multiple interconnections. So there is, as you see, what is called a system bus, and then there is a memory bus, then there is a bridge connecting these. But let's not worry about these details at the moment. We'll look at these in uh, more detail later. So there is some path, some way of information flowing between memory and CPU. Okay, it may not be a simple connection, but they could be. The idea of showing this figure is to say that it could be a complex structure, even connecting memory to CPU. And uh, at an abstract level, we just think that you can have information going from memory to CPU and from CPU to memory. So there is a way to do that. Sorry. Okay, now we also need to connect this pair to the outside world, and that's where input output comes into picture. So there would be another bus, which would be typically called IO bus, and you would have things like disk and graphic display, keyboard, mouse, all these connected to this IO bus. So this is looking more like actually the diagram of a desktop PC. Okay. Now let's look further into this box called CPU. Within this, there are a couple of things. There is what is called register file. So I hope in your logic design course or digital electronics course, you have learned about registers and register files. Okay, register files are nothing but an arrays of registers. Okay, so instead of looking at them individually, suppose you have 16 registers, you think of those as a group where you can specify register number and you can access that register. So this is a register file. And then there is ALU. ALU stands for arithmetic logic unit. What is there in ALU? We'll again discuss in detail during the course. But it is this part which would do all your arithmetic and logic operation. So there is a connection to and fro between these. And there is another register which is special called PC, short for program counter. Program counter is the one which keeps track of the instruction in a sequence. So notice that you have program which is nothing but a sequence of instruction. And if you need to go through those instructions one by one, you need something to track them. So PC is the one which goes from one instruction address to other instruction address and tells you which instruction is being done. So, and this whole assembly consisting of a register file, ALU, PC, and a couple of other things is somehow connected to what we talked of as the bus going to the memory. And there is some block which I'm calling as bus interface. Okay. Now, what does this whole thing do? So let's focus on this part. Okay, CPU and memory. Assuming somehow that information you need from outside world has been brought in, and at the end what needs to be sent out will be sent out. So let's focus on this part. Let's look at instruction which do arithmetic operation. So you'll see some animation. From register, data goes to ALU, ALU does the operation, result gets back to register file. Okay, so typically this is what an instruction for arithmetic operation, add, multiply, subtract, and so on will do. Then you have instruction which will move data between memory and the CPU. Okay, so when we say move data to CPU or move data from CPU, essentially we're talking of registers which are there in the CPU. So there are instructions which will load data from memory to register and instruction which will store data from register to memory. So here is data going from register to main memory, and similarly following the reverse path, data goes from memory to register file. Then there are instructions for decision making. Now what do these instructions do? You would typically be following a sequence of instruction stored consecutively, but somewhere you want to decide, okay, either do this or do that. So when you want to do something different, you need to make PC move to that particular instruction. So normally PC will keep incrementing, but decision instruction will change the value of PC to abruptly something different. Now we have seen that instructions could be written in symbolic form and textual form, but internally they are in some numeric form. So how the instructions are encoded? Okay, so each instruction has to be represented in numerical form, and how these are coded, there may be various ways, and as we discuss instruction, we will look at that. So at this point, so far we imagine a bare computer. That means there is hardware, which where in the memory there is a program, and the hardware can execute that program. All right, but that's not good enough. The memory, we also imagine that data would be moved between memory and register. So imagine that initially the data is in memory, also program is in memory. As the program runs, data is uh, bit by bit transferred to the register operated upon, and the results are brought back to memory. Okay. So between memory and the outside world, there may be communication which we have not seen right now, but they would be something. Now, this arrangement is not enough because you want to work with C, Java, uh, MATLAB, and so on. So, is this bare computer, just bare hardware, uh, in a position to do what we want? The bare computer is like an unfurnished building. Okay, so you have walls, floors, doors, and so on, but you need much more inside these rooms and so on to live and work. So a computer usually comes with hardware, which we talked a little bit, and what is called system software. So you have your own programs to run, but you need support of the system software. So what does the system software do? System software has many programs. You have compilers. Compilers translate programs in the languages of your choice into languages which computers can understand. Okay. So you need different compilers for different languages. All right. So they would be C++ compiler, Java compiler, MATLAB compiler, and so on, which will let you run programs in different languages. Then there are libraries which consist of pre-designed functions. Okay, so pre-designed modules of functions are always available in the library, which can be used in your programs. And you need a software called linker, which puts together your own program plus these library functions. All right. So these functions which are performed by these library modules, the library function, need not be written by you. So these are available to you as building blocks. And linker takes care of linking your program with these library functions. Then there is a loader. The job of loader is to take this link program and place it in the memory at suitable position. So when you're running program, I'm sure you have run program, but you don't explicitly see these things, but these are there. And then you have an operating system, Windows, Linux, Mac OS, and so on, which actually manage all these programs as well as your own programs. Okay, they'll manage the file system. They'll take care of making compilers available to you and other libraries, etc., available to you, and facilitate in running the program, provide a programming environment. All right, now before I pose this question, let me see if you have any queries or questions. So let me turn.
So is there any web page for this course or any website?
Yes, the web page would be maintained on Moodle, so you would all have access to Moodle. You will be able to see lecture slides there. All assignments will be announced there. You'll be able to submit. So Moodle would be the web page. We would use Gradescope for conducting the tests. Um,
And says course policy is also there in the Moodle.
yeah, well, I'll talk a little bit about that towards
Yes.
that. And further details can be added on Moodle. So also, one more thing I wanted to say. Yeah, the recorded lectures would be accessible through MS Teams. So they get stored, and you will find the links on Microsoft Teams page. Any other question? Please feel free to ask question when I halt, or even if you want to interrupt, it is all welcome. So don't need to hold your questions back till I say so. Whenever you have a query, you can ask. And any further question?
Sir, you would be uploading these slides to Moodle as well?
Yeah, the slides would be uploaded on Moodle.
All right, sir.
The recorded videos would also be available. Okay,
All right.
not through Moodle, but through Teams.
Sir, it is, hello, sir.
Yeah, I'm listening.
Sir, it is a bit out of context, but I was just curious to know that would there be any attendance marking in this course? Like some courses do not have them, some do have it.
Yeah, so there's something I have in mind, and towards the end we will see. I'll
Okay.
talk of that. Okay, so let's move further.
Excuse me, sir, I have a doubt in CPU.
Yeah, please go
Sir,
ahead.
we said that the memory is stored in register, but aren't they the part of RAM when we are working on a program?
Okay, so I talked of registers, I talk of memory. Okay, so I took a very simplified view that memory is an array of location.
Yes.
There'll be it'll have, in reality it'll have more complex structure. We'll talk of that. But at the moment you think of memory as a huge array of memory locations. So a memory location can contain an instruction, it can contain a number, piece of data, and so on. Okay, you
Okay.
registers are there for holding the data on which you are immediately working. So
Yes, sir.
if you have two numbers stored in memory, you would bring these to registers, perform the addition, the result is in the register, and then you put the register back into the memory, put the contents of register back into the memory.
Like said, these memories are part of the CPU. Like if we are running a program like and assigning variables, then aren't they stored in RAM or are they part of CPU?
Uh, Registers are part of CPU. Okay,
Oh,
memory is another entity which is, you could say, companion of CPU. So
oh,
when let's say you buy a laptop, okay, it says so many megabytes or gigabytes. So that is a memory. Um, and there'll be different types of memories. It's not just one memory. There'll be different types of memory. What CPU has is registers. So there'll be just a handful of registers, 16 register, 32 register, or 64 register, small number.
okay, sir.
But memory would be in megabytes, gigabytes, and so on.
Yes, sir.
Okay.
And sir, can you please again explain why we can't use bare computer for our work?
Yeah, bare computer expects you uh, to feed a program as a sequence of numbers. Okay, bare computer understands machine instructions, and not even in text form, but in numeric form. So you can imagine how cumbersome it would be if you were to write your program in numeric form. Okay, so firstly you need a compiler which can uh, take the programs which you can conveniently write and transform them into sequence of numbers, or numbers which represent instructions. So that is one thing. Now this sequence of number has to be put in proper location of the memory. So that will be done by loader. But before you could do that, your program would have typically utilized a lot of libraries. Okay, and the numeric code for those library functions would already be available somewhere, and that has to be linked together with your program. So you need all these. You need compiler, you need linker, you need loader, and you need operating system to manage all these. Okay. So operating system manages your files. Files could contain program data, and even the compiler and other things are stored in some files. So as far as operating system is concerned, compiler is another program which has to be run, which has to be brought from some file into the memory of computer and so on. So operating system has several things to do, and without OS compiler and other things and libraries and so on, it'll be very, very hard. Okay, you can write, you can work with small programs of 100 instructions or 200 instructions, but now you would be familiar that you are running programs which are uh, consisting of millions of instructions. Okay, you run some binary, run some app which is in megabytes. Okay, so how does that get run? You need all the system software. Okay, any further questions?
Sir,
Yeah.
sir, please can you tell something about the lab component of this course?
Yeah. Okay, I'll come to that.
Okay, sir.
Yeah.
Sir, before that, so when the compiler convert a program into instructions like numbers and instructions, these
Yeah.
are also stored in memory, na, somewhere in the computer, all the instructions.
Yeah. Yeah.
And
So
the PLU is basically the iterator, which iterates over all these instructions, or what?
yeah. So compiler is also a program which is taking whose job is to take your statements in high level language uh, and convert them into machine language. So now your program would be first of all stored in some file. Okay, that file, the compiler would read that file, bring the contents of the file to memory, then look at the statements, break them down into instructions, and this will the result will be initially in memory and then will get stored in some file. Okay, so what you see directly are the files. Uh, to work with file, you need to bring things into memory, and further down from memory you need to bring to smaller PC, you need to bring to the register file. Okay, so don't confuse between register files and the files in your file system. The file system could be in solid state drive or hard disk drive, right? Which could be in megabytes. So you bring things to memory, and from memory you bring to register file. Register files are small, like 16 register, 32 registers, or 64 registers, something of that order.
Sir,
Yeah.
when a program is being executed, are the instructions stored in memory only, or are they also brought to the CPU and stored in some register or someplace?
Uh, yeah, very good question. They would be, they might be typically register which you may call as instruction register. So it will be brought from memory to that register and used, and interpreted there.
Okay, sir. Thank you.
Okay, so now the question is why should we think of machine instructions? Why can't we design hardware that understand high level language program? Okay, so this is a possibility I'm just throwing up. And also now go back to your course on logic design or digital electronics. We have seen that you can write something in VHDL, and from there we can get a hardware design. Okay, so in fact, it's not only from VHDL. You could actually take a C program with some restriction and synthesize that into hardware details, put that in FPGA, and that hardware would do what the program was supposed to do. So why don't we do this? Anybody has any thought?
So then we have to build different hardware for different languages.
Yeah, that's one problem. You will have to build different hardware for different languages. And if language, next version from 2.1, you go to language 2.2, then that hardware will have to change, which is going to be very expensive.
Sir,
Yes, so it's not a, in fact, go back in history, uh, people have tried building computers which could directly work with uh, high level language. Okay, but those efforts obviously failed. Firstly, you got confined to one language, and secondly, uh, building hardware which could efficiently do that was not so easy. Okay, so you will end up in something which can interpret the high level language, but not very efficiently. Whereas when compilers transform a high level language program into machine language program, they do a lot of analysis, a lot of optimization. And so they are sophisticated programs which can actually turn out efficient code, efficient machine code for given uh, high level language program. Okay, the second option uh, would again be somewhat rigid. Uh, you can have flexible hardware if you're using FPGA, so you can synthesize a program, put that in FPGA, put the hardware design in FPGA, and run the program. One problem here is that synthesis is a very time-consuming process. Okay, unfortunately, you guys have not been able to work with the actual hardware FPGA, but you can take my word for it that uh, although synthesis is possible from program to hardware, but it's a very time-consuming process. The tools which do that take a lot of time. So that's one issue. That every time you want to make a change in the program, suppose you just wanted to add one statement somewhere which you forgot, because you found a bug and you want to make some modification, you have to go through synthesis process all over again, which is very tedious. So that's the main deterrent. The turnaround time of making changes in the program and getting the hardware to run it is very long, and it would be very frustrating to do this way. So if you have a program which has to be run over and over again, then you can spend this time, get an efficient hardware to execute that program. Once you have put in that effort, once you have invested in time, then it can be run very efficiently. And in fact, this is something which is done in some very special cases. For example, you might have heard of algorithmic trading, where uh, you need to uh, work with algorithms and you want to run them very fast to do a good job of the trading. There you need uh, you synthesize hardware accelerators to accelerate those algorithms. Okay, so this approach gets used in some limited manner in very specialized cases. All right. So the conclusion is that for most of the work, we work with machine instructions, but the compiler and other things help us in thinking in terms of high-level languages and allow machine to work with those instructions efficiently. Now, different machines have different machine languages. Okay. So you have different types of computers. You have desktop, laptop, servers, tablets, iPods, smartphones. Okay, all these are doing computation. They are running programs. On the other extreme, you have data centers and supercomputers. So there are different manufacturers which manufacture these. I put some names here. This is not exhaustive list, but some common names which came to my mind. Now, different, some basic principles are same, but different computers have somewhat different languages. Okay, the basic idea may be same, that the basic operation may be add in everyone, but there are other variations. Okay, so what we will do is we will focus on one specific machine language as an example and familiarize ourselves with that. So ARM, I've chosen ARM as the vehicle of this discussion. ARM stands for Advanced Risk Machine, and it's a very popular processor. You find this in embedded systems. Many mobile phones have this, okay, and many handheld computing devices have this. So it's a interesting machine to study. All right. So let's get some idea about the kind of instruction which we have. So typically you think of arithmetic operations where you take two operands and produce one result. In the instruction, the order is fixed. Okay. In case of ARM instruction, this is how you write. Suppose you wanted to perform addition of two numbers, A, and you want to say A gets B plus C. So in the assembly language of ARM and also many other machines, you would say add A comma B comma C. Okay, so add is the operation you are trying to do, and the order ABC is important. In this case, the first one is the destination, and the other two are the operands. For addition, you can interchange B and C. That doesn't matter. But for example, if you're doing subtraction, then you can't. Okay, so depends whether the operation is commutative or not. Actually, you won't write add ABC. You would write something like add R1, R2, R3. Okay, the operands and destination of the result are registers. So this is what you will say. Registers are referred to as R1, R2, R3, and so on. So I'm talking of just three registers. Now, so we have brought in a gap here. In C code, we said A equal to B plus C, but in ARM assembly language, we are saying add R1, R2, R3. So it is the compiler which will figure out which register B goes to, which register C goes to, and which register A goes to. Okay, so associating variables in the high-level language with the registers is done by the compiler. But when you're directly using, and in fact, this is what you will do as lab exercise, to get an insight into assembly language and to understand the purpose of various instructions, you'll do some lab exercises which will involve writing assembly programs. So now you would be wondering why we have instruction like this. The idea of having simple instruction like add R1, R2, R3 is to have efficient hardware which implements those. Okay. So the operands are registers. In ARM, there are 16 registers. It may be tempting to have large number of registers to have more flexibility, but turns out from hardware point of view that a smaller register file is faster than larger register file. Okay. The one implication of this having simple instruction is that complex expressions have to be broken into a sequence. For example, if you had to do addition of three numbers, a equal to b plus c plus d, then you would need two add instructions. Okay. So, for example, let us say b and c are in R2 and R3, and d is in R4. So you will perform addition of R2, R3, put in some other register, let's say R7. And then you can perform addition of R7 and R4 and put in the final destination, which is R1. So R1 is associated with A, R2, R3, R4 are associated with B, C, and D, and R7 is some temporary register holding the intermediate value. Another example, you have a subtraction followed by addition in this expression, okay? But since there is parenthesis around A and B, you will first perform addition. Once again, let's say R7 is being used as intermediate value holder, and then you perform subtraction. So here order of R6, which holds F, and R7, which holds the sum of A and B, is important. Okay, you can't say R5, subtract R5, R7, R6. But in addition, you could interchange the operands. So now let's look at the picture which has some of these major blocks of the processor.
Excuse me, sir.
Yeah.
What is a RISC machine?
We'll talk of that.
All right.
So you can hold on question. I know in ARM is an abbreviation for advanced RISC machine. So what is RISC? We'll discuss at a later point of time.
Excuse me, sir. Sir, can an ARM code like this exist? Like add R1, R2, R1?
Yeah, this is see, you will, let's say, okay, so there is a program called assembler. All right. I forgot to mention that. The job of assembler is to take instruction in this form, in symbolic form, and convert them into numeric form. Because directly writing in numeric form will be very tedious. The job of assembler is not too difficult. Okay, it is kind of one-to-one mapping. It takes one instruction, finds out its code, takes another instruction, finds out the code, and so on. So in your lab exercise, you will write instruction in this form, and you will have an assembler which will convert this into numeric form before the instructions can be executed.
So one doubt, sir, how does it know which registers are do not have any currently holding? I mean, are not holding any value currently?
Yeah. So when you know when you're doing assembly language programming, you have to figure out, you have to keep track of which register is occupied, which is free. Okay. But in real scenario, when you are working with high level, suppose you had to give this code, you have to work with this code at C level, right? Then the compiler will figure out which variable gets mapped to which register.
Okay.
So compiler keep track of which registers are free, which are occupied, which have been mapped to some variable, which have not been, and accordingly generate code. But as an assembly language programmer, one has to keep track manually.
Excuse me, sir. So in this one instruction add R7, R2, R3, this is 32 bits. And
Yeah.
Each register can be, I think, represented by 4 bits. So does the add bit, like add instruction, like does that take 20 bits and then the rest of them take 444 each or something like that?
Good question. We'll answer that in detail later. So for let me just rephrase the question. So question is uh, about how does this assembly instruction relate to the machine code? Okay, so that number, the machine code, will have to specify these four things. One is which three registers we are talking of, and which operation we want to do. Okay, so the person who asked the question quickly figured out that if you are talking of 16 registers, then specifying that register requires only specifying each register requires only 4 bits. So you would that numeric code of this instruction will utilize 4 bits each for these three registers, and would need some more bits to specify that it's an add operation. Now the question was that if the whole thing is in 32 bits, then do we need 32 minus 12, 20 bits to specify add? Uh, so again, one part of this is clear that these registers will be specified in 4 bits each. But how does we specify, how does add part get coded? We'll see that later. Okay. So let's not worry about that right now. Okay. So here are the major blocks in the whole system. You have memory, you have CPU. Within CPU, there'll be what is called data path, where actually computation get done. This includes register files, ALU, and so on. Controller control would be like a finite state machine, which is making it step through different steps. And of course, you have input output modules. So the registers are here in data path, and you have a bulk memory sitting somewhere else. So you can think of relationship between program and where different things get stored. Scalars could be mapped to registers. Okay, scalar means single variables which can't be broken further, like just one integer, or one floating point number, or one logical value. Whereas structures or arrays, these have to reside in memory. You can't fit, suppose you have an array of 1,000 integers, that obviously can't fit in register. It has to be in the memory. So let's look at memory organization. Memory is typically, and also in case of ARM, organized in terms of groups of 8 bits, which are called bytes. Okay. So you could view conceptually memory as a large single dimensional array where each element is a byte and has an address. So a memory address is an index into the array. The reason we are talking of just 8-bit is that you can access, you have a finer resolution. You can access 1 byte at a time. But groups of 4 bytes would form one word, which is 32 bits. The address itself is 32 bits, which means you can have 2 raised to power 32 bytes. And the addresses go from 0 to 2 raised to power 32 minus 1. Since you have 4-byte words, the addresses of words are 0, 4, 8, and so on. So they are multiples of 4. And you have 2 raised to power 32 words. Bytes within a word can be ordered in 2 different ways. One is big endian byte order, where you start from, so to say, left side or the most significant side. So you could number bytes as 0, 1, 2, 3, 4, 5, 6, 7, going from left to right. And the other is little endian byte order, where you do the opposite. Okay, so different computers follow different orders. Some follow big endian order, some follow little endian order. You could also have words which are not aligned, where the address of word is not a multiple of 4. So for example, you can think of word starting at address 1. Okay, and following the little endian byte order, this word would be consisting of byte 1, 2, 3, and 4. So all the memory would be physically organized in terms of aligned words. Okay, this is a logical word which is not aligned with the physical word. Okay, 1, 2, 3, 4 still form a logical word consisting of 4 bytes, 4 consecutive bytes, but it is not aligned with the way bytes are physically organized in memory. Okay, so I talked of arithmetic instructions. Let me talk of instructions to access memory. So you have load store instructions. For example, we want to pick up element number 8 of an array A. Okay. So suppose the array begins at address 100, and array consists of integers, each occupying 4 bytes or 1 word. So A0 has address 100, A1 has address 104, and so on. A8 has address 132. So when I say has address 132, it means it consists of 4 bytes numbered 132, 133, 134, and 135. So you will use an instruction called load. LDR stands for load register. And you can see that there are 2 registers involved, LDR, R1. So now these brackets and hash, all these are part of the syntax. So we'll see that in detail in due course. So now what we are saying here is that R1 is where R1 corresponds to V here. So we want to get some data from memory, put in register R1. Okay, and where is the data located? It is an address which is found by taking contents of R2 and this number 32, adding them together. So this allows you to have one base address, that is the starting location of array, and an offset, which you add to the base and get the. So here, assume that R2 has the base address, which is 100 in this case, and 32 is the offset from where you want to make an access. Okay, I think I'll skip some part. We'll talk of that later. Let me go to some administrative stuff right now. Okay, so something about the lab and so on. So in the lab, you'll be executing programs. By the way, lab will have some initial exercises which involve assembly language programming. Idea is to familiarize you with at least one assembly language, okay, to get some insight. And how would we run this program? We'll use a simulator called ARM-Sim. So actually, you can run this program on actual ARM machine, but for the purpose of our lab, we'll use a simulator called ARM-Sim. We'll give you more detail about this later. This simulates one particular ARM architecture. ARM also has a series of versions, and we'll talk of one which is supported by this. So this includes an assembler and simulator. It allows step-by-step execution and breakpoints. It can display contents of registers in memory, supports input-output. I like to mention this book, which we will follow as a textbook. We will be covering these chapters except for the last one. Broadly, evaluation plan is that lab part will have 30% of the weightage, and rest would be made up by tests and quizzes. I don't know how many minors will be there, probably only one. So I'll look at that, whether there are two minors or one minor. And out of 70%, there'll be something like 15% for quizzes or assignments. They could be theory assignments. The passing requirement is that you need 30% in the theory part and 40% in the lab part. Okay, people are concerned about attendance policies. So there is some strange attendance policy. I want 100% attendance, subject to timely and satisfactory explanation evidence for any absence. If you need to be absent, let me know and tell me what keeps you away. Okay. So this policy is there only when you. I mean, I look at this only when you come to me for some special request, like you missed some test, you want an alternative, you missed something else in the lab, or you get an E grade at the end or I grade, and you want a retest. So that's when you look at that attendance. Otherwise, you are free. You may attend, you may not attend. Okay, but if you have missed out, then you lose the right to make any special request. Okay, let me stop at this. I can quickly address any other question if you have. I'm sorry, what is the time? It's 10:30. Oh, I think I still have time, so I need not skip what I thought of skipping. I thought the time is getting over. Okay, yeah, we were here. So as a sorry for this confusion. We have another half an hour. Uh, the way this instruction is designed is to allow you to specify address in two parts. One is like the base, another is an index. This facilitates making access to arrays, for example. Now you may be wondering that why we have 100 in register and 32 as a constant. So you basically you're adding contents of a register and a constant. You could have done this way, that R2 has the offset, register has the offset, and the base is specified as a constant. Okay, the problem with this would be that uh, the range of constants you can have within an instruction may be limited. Okay, and so if the address, starting address of the array or the address of A0 is large, then specifying that as a constant may not be feasible. Okay, so typically what is done is that the base is put in the register and the offset is put as a constant. So there may be, of course, situations when even the offset is large and can't be specified as a constant, or the offset is itself in a register. Okay, instead of saying A8, you want to refer to AI, where I you don't know in the beginning. I could be a variable. Then, of course, you can't do this way. You need to actually perform addition to get the address, right? But there are situations where you can manage in this manner. You take a base and a small offset and perform load like this. So now let's look at a statement like A8 gets A8 plus H. So here there is going to be a load and there is going to be a store corresponding to left hand side. The code would be load register R1 R2 hash 32. So this index 8 is translated into 8 into 4 32 as the offset for 8th element. Assuming that R2 has already the base, this instruction will bring value of 8 into register R1. So R1 is being used as a temporary register here. Assuming that H is stored in, let me get the laser pointer. H is stored in register R3. Okay, you perform addition of R1, R3, get R1. The result is again in R1. And then this can be stored. So store instruction is very much like load instruction. Just the direction of movement of data is different. Any question on this?
Excuse me, sir.
Yeah.
Sir, in the previous example, are we storing the result in R1 or R2?
In load instruction, the first thing is the destination, and the second thing is the source. In store instruction, it is opposite. R1 is the source, and R2 combination with 32 is a destination. So load is from memory to register, store is from register to memory.
Okay, thank you, sir.
Sir, I wanted to ask that what is the need for loading and storing it? Can't we just add it on the location itself?
Okay, there are some machines, some processor which don't involve registers. Okay, you could directly specify two memory addresses or two operands and perform addition. So there are pros and cons of that approach. The approach which is followed in this processor is whatever you want to do in terms of arithmetic. You first bring the operand to register, perform arithmetic, store the result back. Now, if the sum of 8 plus h had to be further operated, then need not immediately, suppose it was like A8 equal to A8 plus H plus G. Okay. If another addition was required, so you will do that addition before you put the result back in A8. Okay. Or on the left hand side, there was something else, some other scalar, which further participated in other expressions. You will not store the result immediately. You will try to keep it in register as long as you need it, and when you're done, then you put back in memory. But we will see alternatives where things are done differently. Here you have separated the instructions which do arithmetic and instructions which do load store. There are so actually somebody asked question, what is RISC? RISC is a processor design philosophy. We'll talk of more of that. Where one of the idea is this, that you have different instructions for doing memory access and arithmetic.
So is the only difference between load and store instructions the direction of movement of data?
Exactly.
So then
Yeah.
why do we have two instructions? Like we could just do the same thing with just load.
Okay. Yeah, you would still need two instruction, or instruction you could have, let's say, all right, let me just imagine. Suppose you had an instruction like which we call as memory access, and specify two things, a register, a memory, and one more argument you will specify as direction of movement. So you could maybe combine those two instructions into one instruction, distinguished by yet another parameter. But this is a, uh, this also reflects a style of design. They have designed two different instructions. When it comes to machine code, you'll find that there is a lot of similarity in these two instruction codes. They differ only. Uh, if I remember correctly, just one bit is different in the code of load and store.
Sir, when we load something, do we load it from like the memory to the CPU register? Like, is that what we are
Yeah.
doing in?
Load
So,
means load from memory to CPU register, and storing means store from register to memory. So it's like I think you are all familiar with download and upload. So load is like download, and store is like upload. If that helps you in understanding.
so like the second argument will be the address in the memory, right? So I don't think so.
Right.
We can switch load and store like Somil was saying.
No. I mean, it's a matter of syntax and coding. The previous question was valid, that you could think of a single instruction and put in an argument. You could write uh, memory access R1, comma, whatever is there in the square bracket, comma, one more thing you will write which indicates direction of movement. Okay, so it's one more complex looking instruction. And actually, in terms of the binary code, this is what is happening, as we are going to see later. Okay, so moving further now, here is an example which will illustrate memory access, load store, uh, and also use of a temporary variable. So this code we know does interchange of two elements, and in machine language, in assembly language, suppose R2 has address of V0, that is the base of the array. R5 has, now I'm using this at the rate sign to indicate it's a comment. R5 has K, R4 has this constant 4. So getting VK, loading VK into temp means that first we do address calculation. We multiply R5, which is K, by R4, which contains constant 4. Okay, because the offset has to be 4 times K. So we do this multiplication. We add this offset. We are assuming that K could be large, so we can't specify. And secondly, it is coming as a result of this computation. So we need to explicitly perform addition of offset and the base, add R3 and R2. And we put it back in R2. We could have put in a different register also. Then perform load. Okay. Now, since entire address has come into R2, the offset part is 0. Okay. So we have loaded VK into temporary location. The next statement was VK plus 1, V of K plus 1 is assigned to VK. So we need to now load VK plus 1. And you can see the role this second part is going to play here. We are still using the same base R2 and have put an offset of 4. Okay, so now the memory location of VK plus 1 will be addressed, and that is loaded into R7. So now VK and VK plus 1 both are in 2 registers. So all that we need to do now is store R7 in the address of VK and R6 in the address of VK plus 1. Okay, so this is the code. I talked about load register, store register. So these deal with transfer of one word between memory and register. There are similar instructions for transferring smaller or larger amounts. LDRB, STRB. These you can read the load register byte, store register byte. You can talk of half word, which is 2 bytes. Okay. So LDRH and STRH. Next, let's look at some decision-making instructions which alter the control flow. So there is an instruction called compare, and compare in conjunction with conditional branch instructions like BEQ, BNE can do the job. So I'll illustrate that. Here we have a small code fragment from C. We're comparing I and J. And if I is equal to J, then we perform this addition, put that in H. And after this if instruction, if statement, there is K equal to K minus I, another assignment statement. So how do we do that? Assume that I and J are in register R1, R2. We use compare instruction, compare R1, R2. But where is the result? The result is retained in some flags, and the instruction following it will test that flag. So BNE stands for branch if not equal. If the result of previous comparison said that the two operands were not equal, then you go to instruction which is labeled L. So instructions can have labels. In assembly languages, the instructions can be labeled, but in machine language, these labels will basically correspond to some addresses. Okay, but for convenience, we say that branch if not equal to label L. Okay, so that means if R1, R2 were not equal, then you will skip add instruction, go to subtract, which is labeled as L. Okay, HI plus J is translated as add R3, R1, R2. So R3 is holding H, and the subtract statement is subtract R4, R4, R1. So as we had seen, I was in R1, K is in R4, and we have these 4 instructions representing the code on the left. Another example where you have else part as well, we would need an unconditional branch instruction also, which is just abbreviated as B. So here you have if I, okay, this should have been comparison sign equal equal. If I equal to J, we have this addition done, otherwise this subtraction done, and in both cases K equal to K minus I is done. So you have comparison as previous case. Branch if not equal to label 1, that is this instruction. Otherwise, you perform this addition that corresponds to H equal to I plus J. And after having done that, we want to skip the subtraction which corresponds to H equal to I minus J. So here we have unconditional branch, which takes you to label 2. So now look at the flow. You will follow one of the 2 paths. Compare this branch, this addition, this branch, and then this last subtraction. That's one possibility. Other is comparison, this branch, but we don't actually, yeah, we carry out this branch, go to label 1 and then label 2. Okay, so as you can see, either this add instruction is done, add R3, R1, R2 is done, or subtract R3, R1, R2 is done. So you can have other conditional branches like BLT, branch if less than, BLE, branch is less than or equal to, GT, GE, and so on. So now finally, let's write a simple loop which performs sum of array elements. Is there a question?
Yes, sir. So why do we need unconditional branching? So if we just write down the code as it is, wouldn't that be executed?
So if you don't have this unconditional branch in this code, then subtract R3, R1, R2 will be done always. Okay, so if you don't have this unconditional branch, you are either skipping this add R3, R1, R2, or you are doing it. But rest of it gets done in both cases.
Yes.
Hello, sir.
Yeah.
So when the instruction BNE lab1 was prefetched, then it will go to level 1 subtraction R3, R1, R2. Then will it be returned back to that one or continue from that onwards?
It will continue from that point onwards.
Okay, so then level 2 will be performed if it's instructed
Right.
or not.
Yes.
Okay.
Okay. Okay. So I've written this loop for summing elements of array in a somewhat low level form. I've not used a loop as such, but I'm using a branch, a go-to statement. So so that index, incrementation, and comparison of the final value, these are all done explicitly. Initialize s, which will hold the sum to 0. Index initialize to 0. Then you do s equal to s plus ai, increment I, and if I is less than n, go to this L. Okay. Let's see now corresponding assembly instruction. We are initializing R1, R2 to 0. These correspond to S and I. Okay. Then address of AI is calculated by taking I, which is an R2, multiplying by R7, which contains 4, and you get the offset that is added to R4. Assume that R4 was the base. Okay, you get the address in R3. Then load AI into R5, which is temporary location. Add that to the sum value, current sum, R1, put that in R1. Okay, increment I, check if compare R2, compare I with R6. Assume that R6 contains the value of n with which we need to compare. And if R2 is less than R6, branch to L. Okay, so loop will be implemented by this branch instruction. Okay, you do it repeatedly, and when this condition changes, then you come out. Okay, now we can make this more efficient, particularly the way address is being calculated. Since we are adding consecutive locations of array A, we can, okay, this is showing the correspondence, which I'm sure you would have noticed already. I would like to now change this program to make it more efficient. Okay, rather than doing multiplication and address calculation in that manner, we'll keep suppose we keep a pointer, okay, which is initialized to the first location of A, and then we need to simply increment the pointer. This will avoid multiplying by 4 and then adding it to the base. So in assembly language, we have another register which holds this pointer initialized to R4, which contains the starting address of array, and then we can directly do a load. Okay. All we need to do is R3 is incremented by 4 every time. So P++ means add R3, R constant 4. I++ means add R2, constant 1. And then rest is same. So in fact, if you uh, look at it now, the index is being used only for counting the loop iterations. Okay, it is incremented, initialized here, incremented here, and compared with R6 here. If we change this further, we compare this pointer with the final value of the pointer. Instead of comparing I, we can get rid of I altogether. As you can see in this code, there is no I. We have the final address, which is P plus. So to this pointer, we add 100, which means actually we'll be adding, in terms of address, we'll be adding 400. And then P is compared with Q. So R6 holds the Q, which is same as R3 plus 400. Okay, and comparison is done with that. So this makes it more efficient. In order to run this program, you will have to take care of defining a few more things. So you need to specify, for example, where is this array stored? You need to make the assembler understand that there is an array which has bulk space. So you would notice here I have brought in something which look like instruction, but there is a dot preceding those. Dot eq, dot text, dot data, dot space, dot n. So these are assembler directives. These are not executable instructions. These are sort of commands to assembler to do something. So dot text specifies that the code is beginning here. Dot data specifies that data is beginning here. After all, code and data both reside in the memory. So you need to mark out the space for those. And we have named the array as by putting a label AA. Dot space indicates that this is you are allocating some bulk space here. That is the size. So you are trying to say that 400 bytes of data are going to reside here, where the address would be, starting address would be specified by would be figured out by the assembler, but it will leave out space of 400 bytes. That this one can be ignored at the moment. This is basically to transfer the control between the simulator and your program. So we'll talk of that later. The instructions for installing ARM simulator and running the simulator will be given to you. We'll put some information on Moodle, so you'll be able to write programs and run these programs. So we'll announce a lab assignment soon, which you would need to do on ARM simulator. So look for instructions for downloading, installing, and working with this simulator. Okay, I'll stop at this point. Yeah.
Hello.
I had a doubt.
Yeah. Go ahead with your question.
Okay, sir. So,
of exam, timings of lab.
Yeah, labs, there are no fixed timing. Since we are all doing online, you are sitting at different places, so there are no specific times. Assignments will be given, there will be deadline. You do them at a suitable time and submit it. Okay.
Hello, sir.
We'll be available for interaction. You can send us messages and mails to me and TAs. I'll introduce the TAs to the class, and we can communicate electronically. Yeah.
Hello, sir.
Any
So
other?
is this
Yes. Go ahead.
available for Mac OS as well? Is this simulator available for Mac OS?
Yes, it is available for macOS also.
Okay, sir.
Hello, sir. So,
Yeah.
basically, if a register, the 16 registers are all 32 bits. So, if we
Hmm.
have to store a large number which is 32-bit in one of those registers, then we have to write an instruction which has the move instruction and then a 32-bit number. So, how can that fit into a 32-bit instruction?
Uh, See, the instruction within instruction you cannot fit a 32-bit number. Okay, so we need to do some other tricks. We'll talk of those. Yeah, so it's a good question. Um, how can an instruction specify a 32-bit number? So the constants which are part of the instruction can't be 32-bit. They are small constants. So if you need to deal with larger constants, how do we do that? We'll discuss. Okay.
Hello, sir.
Yeah.
So I wanted to know about registration to this course. I had mailed you earlier.
What's your name?
So Ishan, Ishan Watts.
Ishan, I have noted your request and I'll take it up with Chairman Grade and Registration. So you keep attending classes and I think next couple of days I'll have it worked out.
Okay, sir. So since Act Drop was closing on 11th, so
Yeah,
can you
we will
please?
take care for that.
Okay, okay. Thank you, sir.